A matrix is called normal if it commutes with its adjoint. When I say adjoint, I'm really talking about in the complex vector space context. So a matrix is called normal. The adjoint of a matrix in complex vector space is it's transpose and then you take complex conjugate, right? And it's very customary to, instead of writing bar and then t all the time, we just write a with a star. Okay? So a star means you take the transpose, which means you flip the matrix along the over the diagonal. Here's the diagonal, and then you flip it. And then you take the complex conjugate, that's called a star. And instead of saying all this, another definition would be just A is normal, means A and A star commute. So A times A star is same as A star times A. If that's true, then it's called normal. Which doesn't sound like a hard thing for a matrix to satisfy, right? Let's see. What if I have something like 1, 1, 2, and then 0? What if, is this normal? Let's check if this is normal. What is A star? Well, you have to take the transpose. So 1 goes here, 0 goes there. The diagonals stay in place. And then you also have to take the complex conjugate, but all these numbers are real, so it's not a complex conjugate. The complex conjugate doesn't do anything, so it's nothing happens. Now, what is A star? It would be 1, 1, 0, 2. And then 1, 1, 0, 2 this way. Okay, so across down gives you 2, across down gives you 2, across down. Okay, so that's what you get. And then on the other hand, what's A star A? You have 1, 1, 0, 2, 1, 1, 0, 2. Oh, so it's not normal, because if I multiply this, you get 1, right? And this has 2. So unfortunately, it's not normal. 1, 1, 4. Okay, so it's not normal. Theorem 1, if V is an eigenvector of a normal matrix A with eigenvalue lambda, then V is an eigenvector of A star, okay, with eigenvalue lambda bar. So let's think about that. Proof. What is an eigenvector? That means when A is applied to that eigenvector, it doesn't change direction, it only changes its size, right? And the change in size is done by a multiplication by a number. That number is called the eigenvalue. Right? And I can rewrite this as AV minus lambda IV equal to 0. So I'm just rewriting V as IV. Okay. and I moved everything to the left side, and then I can factor the v out and rewrite this as a minus lambda I v equals to 0. Now what happens is that if I take the determinant of this for an eigenvalue lambda, that means the determinant is 0, so that this matrix will be not full rank. Because it's not full rank, it has some null space. So there's definitely some kind of a vector which gets killed by this matrix. Okay? So that's what we call the eigenvector. And that and then we now use the following fact that if I take a minus lambda I v, a minus lambda I v, inner product with itself, that would be the norm of a minus lambda I v squared, right? That's true for any vector, but I just want to use the inner product for this question. Okay, so a vector inner product with itself is the norm squared, but we just said that this is 0, so this is going to be 0 norm squared, but the norm of a 0 vector is 0. That's what you get. Okay? Now, let's try to do the following. I can take this matrix and move it to this other side, right? By doing what? Taking the adjoint. So that was one of the things that we worked hard on last time. The adjoint of a matrix allows one to move from one side to the another on the inner product. So this is going to be now equal to v a minus lambda I star, okay, and then a minus lambda I v, and then you still have to think about what this is. Well, so this is transpose and conjugate, right? So you get a star. You have to take a star. But then, what's the identity that you what do you get if you transpose the identity? The identity is already a diagonal matrix, so transpose doesn't do anything, right? So the transpose is not going to do anything on this. However, if lambda is a complex value, the complex conjugate will do something, which is lambda bar I, right? So this is what you have. But then, if you expand this out, right, you're going to see that at some point you're going to get a star times a, which we can switch out to be a times a star. And then any matrix commutes with scalar multiplication and also the identity, right? So if you have identity times any scalar multiple, this commutes with any other matrix. So this with this will commute, this with this will commute, these two will commute. These two, by definition of normal, commutes, right? So I'll spare you the details, but if you expand this out, FOIL this out, and then you factor again after commuting them, you end up saying that this is same as these two things switched. So you have a star minus lambda bar I, and then a minus lambda I here. These two things commute from being normal, because normal means a and a star commute. And now you're going to move this to this side, again using the adjoint. So if you use the adjoint to move it to the other side, then the same reasoning applies, giving you this. Oh, But now look at this. This is same thing, inner product with itself, isn't it? In that case, you always get the norm squared. Just A star minus lambda bar I squared. Okay. And then oh, but then this has to be equal to 0. That's what we started with. This has to be 0. And a size of a norm squared will be 0 if and only if that vector is a 0 vector. So all this argument shows that A star minus lambda bar I times V equal to 0. Now you multiply this out and move this V to the other side, and you get A star V equal to lambda bar V, which is what we are trying to prove. V is indeed the eigenvector of A star with the eigenvalue lambda bar.